All right, today we're going to pull back the curtain on some real magic, the hidden force that pretty much runs our entire digital lives. I'm talking about data compression. You know, it's the ultimate unsung hero that lets you stream movies, zap photos across the globe, and download massive files in like seconds.
I mean, seriously, have you ever stopped to think about it? How in the world does a full-length, 2-hour movie squeeze onto your phone? Or how does a gigantic folder of files shrink down into one tiny little zip file? Yep, you guessed it, it's all data compression. So how does this digital wizardry actually work? Well, let's get into it.
Okay, so to really get our heads around this, the first thing you need to know is that compression is basically split into two big families, or kingdoms if you will. You've got lossy and lossless.
So, on one hand, you've got lossless. Think of this as the perfectionist. It makes a perfect, exact copy of the original. Every single bit is preserved, which is absolutely crucial for things like text files, code, or databases. I mean, you can't have one wrong character in a spreadsheet, right? That would be a disaster. Then, on the other side, you've got lossy. This is more like the practical artist. It knows you won't notice if a few pixels in a photo are slightly off, or if a sound frequency you can't even hear is missing, so it cleverly throws away that extra, unnoticeable data. The trade-off? A tiny, tiny bit of quality for a huge reduction in file size. It's perfect for photos, music, and videos.
So whether it's lossy or lossless, how do these algorithms actually do it? How do they perform this incredible shrinking act? Well, it's not real magic, but it kind of feels like it. It's actually a really clever two-part trick.
And here it is, the secret recipe for basically all data compression. It comes down to two steps: modeling and coding. That's it. These two ideas working together are the foundation for everything we're talking about. Okay, so think of it like this. The first part, the model, is like a detective. It scans through all the data, looking for patterns, for repetition, for things that show up over and over again. Its whole job is to figure out the structure and predict what's coming next. Then, once the model has done its detective work, it hands its notes over to the encoder. The encoder is the super efficient scribe. It takes the patterns the model found and comes up with a super compact way to write them down. It's a perfect partnership. One finds the patterns and the other finds a shorthand for them.
All right, let's actually start with the second part of that recipe, the coding. And to do that, we have to go back in time a bit, right to the very beginning of the information age.
So, back in the 1940s, this absolute genius named Claude Shannon basically invented the field of information theory. He gave us this idea of entropy, which is a fancy way of measuring how much real, unpredictable information is in a message. But it was a guy named D.A. Huffman who, in 1952, took that theory and turned it into something incredibly practical. He created a method for coding that was just a breakthrough. Seriously, his work became the foundation for compression tools that people were still using decades later.
See, before Huffman, things like the ASCII code gave every single character the exact same amount of space. An E took up the same number of bits as a Z, and Huffman looked at that and thought, well, that's just wasteful. His big idea was so simple but so powerful. Why not give the most common letters shorter codes and give the rare letters longer codes? It's a simple concept, but it was absolutely revolutionary.
And you can see it right here. The letter E, which is all over the place in English, gets a nice short 3-bit code. But Z, which you barely ever see, gets this really long one. Now that might not seem like a big deal for one letter, but imagine a whole book with millions of characters. Just by doing this, you can often shrink a text file by 25, even 40%. That is a massive amount of savings, just from one clever idea.
So how does the computer figure out which codes to assign? Well, it builds this cool thing called a Huffman tree. And the way it does it is actually pretty neat. It starts from the bottom up, pairing the least common letters together first. By doing that, it guarantees that the most common letters end up at the top of the tree with the shortest paths. And that means they get the shortest codes.
Okay, so Huffman coding was a total game changer, no doubt. But it still had one limitation. It looked at the data one character at a time. The next huge leap forward in compression came from a totally different way of thinking about the problem. It's called the dictionary approach.
And the idea behind it is just beautiful in its simplicity. Think about it. Why would you write out the same long phrase like the United States of America over and over again in a document? Why not just write it once and then create a little shortcut for it every other time? That right there is the core idea of dictionary-based compression.
So the most famous algorithm that does this is called LZ77, created by two guys named Ziv and Lempel. Here's how it works.
It keeps a little memory of the text it just saw. They call it a sliding window. As new text comes in, it checks, hey, have I seen this exact string of words before in my window? And if it has, it doesn't write the whole thing out again. No way. Instead, it just leaves a super short pointer that basically says, hey, just go back 50 characters and copy the next 10. It's like telling someone, you know that thing I said a minute ago? Say that again, instead of repeating the whole sentence.
And I guarantee you have used this, probably without even knowing it. This exact kind of dictionary-based magic is what powers the classic PK zip file. It's in ARC files, Unix tools, it's pretty much everywhere.
So let's bring it back to our recipe, modeling plus coding. In this case, the model is doing all the hard work, building that dictionary of repeating phrases as it goes. And the coding part? Well, it's super simple. It's just writing down those little pointers instead of the actual text. Incredibly fast and incredibly effective.
So at the end of the day, it really isn't magic. It's just this incredibly clever two-step recipe. It doesn't matter if you're using the statistical approach of Huffman or the dictionary method of Ziv and Lempel. The formula is always the same. First, find the patterns. Then, find a really efficient way to write them down.
You know, data compression is what made our modern digital world even possible. It's what allowed us to shrink space and time. But now, we're creating data at a rate that is just mind-boggling. It's exploding. So the question is, what's the next great shrinking idea going to be? What will it need to conquer? That's definitely something to chew on.
Impress Me tutorials.